All right, guys, Mr. Antonucci here, and in this section, we're going to talk about antiderivatives. So, we've already learned that for a differentiable function, there is a corresponding derivative. We call it f prime. Now, let's think of that kind of backwards. If you have a given function f, is there another function whose derivative would end up being f? That is it possible to have a function, let's call it capital F of x, such that capital F prime of x equals f of x? Well, such a function does exist, and it's what we call an antiderivative. So a function capital F is called an antiderivative of the function f if capital F prime equals f for all x in the domain of f. So an example of an antiderivative is, um, let's take the function f of x equals 2x. Capital F would be x squared, since the derivative of x squared is 2x. But capital F of x could also be x squared plus 3, because the derivative of that is also 2x. In fact, it doesn't matter what number I add or even subtract from x squared. When I take the derivative, as long as you add or subtract a constant to the x squared, the derivative is going to be 2x no matter what. So, in general, we can write the antiderivative capital F of x as x squared plus c, where c is a constant. So the antiderivative of 2x is capital F of x, and we write it as x squared. So there are no other antiderivatives besides the form x squared plus c. And that has to do with this corollary that says if the functions f and g are differentiable in an open interval a and b, and f prime equals g prime for all those numbers, then there's a number c for which f equals g plus c on that interval. Okay, that's just showing that the antiderivatives are equal up to a constant. So we can summarize it the following way. If a function capital F is an antiderivative of a function f defined on an interval I, then any other antiderivative of f has the form capital F plus c, where c is an arbitrary constant. Because graphically what happens is the graph of capital F of x, let's just say capital F of x is x to the sixth over 6. That'd be like the antiderivative of x to the fifth. Um, when you add or subtract different constants, all that does is vertically translate the function up and down, however many units, but the derivative is still going to be the same, and that represents the slope of the curve at any x value, and it would still have the same slope. So let's go ahead and look at an example here of finding antiderivatives of a function. So we want to find all antiderivatives of, so for part A, f of x equals 0. Since the derivative of a constant function is 0, all the antiderivatives of f of x equals 0 are of the form capital F of x equals, we would just use capital C, where C is a constant. Okay, because the derivative of a constant is 0. We don't know what the specific number would be, but in general, the antiderivative of 0 is going to be a number. So for B, if you have g of theta equals negative sine theta, you just think, whose derivative is negative sine? Well, capital G would be cosine theta plus capital C, because the derivative of cosine is negative sine. And as long as you add any constant to cosine theta, the derivative of that constant will go to 0, and then the derivative ends up being just G. Okay, so now for part C, the antiderivative of x to the half is going to be capital H equals 2 thirds x to the 3 halves. And this is because um, the derivative of 2x to the 3 halves is 2 or 2 thirds. Um, then you would bring the 3 halves down, and the 3 halves subtracted by 1 would give you x to the 1 half. So all the antiderivatives would be of the form 2 thirds x to the 3 halves plus c. And we'll talk a little bit more about how to figure this kind of thing out, because you may wonder how we figured out that 2 thirds x to the 3 halves would be the antiderivative. So there is a link here between differentiation and antiderivatives. Because remember, the power rule is that x to the n, or x to the a, the derivative would be a times a to the a times x to the a minus 1. Differentiation is going to reduce the exponent by 1. Well, when you anti-differentiate, it inverses the process. So that would suggest if we reverse that process, we're going to increase the exponent by 1. That's how we get the exponent to be 3 halves, because 1 half plus 1 is 3 halves. So the factor 2 thirds is needed so that when we differentiate, that to check when the 3 halves comes down, it cancels with the 2 thirds, like it did right here, resulting in x to the 1 half. So the antiderivative is 2 thirds x to the 3 halves plus c. Now we're going to formalize that with a basically the power rule for antiderivatives. So if you have little f is x to the a, then the antiderivative is, well, you reverse the process that you did. So for differentiation, so you add 1 to the exponent and multiply by the reciprocal of the new exponent. Okay, or divide by the new exponent, and then add your plus c. Now this is in effect as long as the exponent of little f is not equal to 1 or negative 1. Because if you have f of x equals x to the negative 1, and you follow this process, capital F would be x to the 0 over negative 1 plus 1, which is 0, which is undefined. But you should remember that the derivative with respect to x of natural log absolute value x is 1 over x. And remember, x to the negative 1 is 1 over x. So all antiderivatives of f of x equals x to the negative 1 are of the form capital F of x equals natural log absolute value x plus c. Okay. So this table below here that I'm going to reveal now includes those results along with several of the other antiderivatives from other common functions. So you definitely will want to know these for the AP exam if you're taking the exam. So this is the antiderivative of 0, antiderivative of 1, antiderivative of a power function, antiderivative that results in natural log. Antiderivative of e is just e to the x, but don't forget the plus c. A to the x is a to the x over natural log a. Sine goes to negative cosine. Cosine goes to sine. And then the other trig functions, and then the inverse trig functions here as well. One of the tricks that, or the hints, or the techniques or tools that I use to remember the antiderivatives of the trig functions is that if the antiderivative starts with a co, it should also start with a negative. So the antiderivative of sine is negative cosine. And then cosecant cotangent, the antiderivative is negative cosecant. And if you have cosecant squared, the antiderivative is negative cotangent. So this is pretty much just reversing all the differentiation rules that we have learned. So these next two theorems are going to be consequences of the properties of derivatives and the relationship between derivatives and antiderivatives. So if functions capital F1 and 2 are antiderivatives of little f1 and little f2, then if you add them, that's going to be an antiderivative of adding little f's. If you subtract them, that's going to be the antiderivative of subtracting little f's. This is just like the sum and difference rule. Um, so in essence, you can add and subtract antiderivatives. And then the constant multiple rule, if you're multiplying a function by a constant, then you can multiply that constant by its antiderivative. So with that, we'll look at this example here where we want to find all the antiderivatives of f of x equals e to the x plus 6 over x squared minus sine x. So since this is a sum, we can find each antiderivative separately and then add them together. So for example, the antiderivative of e to the x is e to the x, technically plus c. 6 over x squared would be 6x to the negative 2. Its antiderivative, well, we're going to add 1 to the exponent, so that becomes negative 1, and then multiply by the reciprocal of the new exponent, so negative 1. And that constant of 6 stays there, plus c. So that's going to end up simplifying to negative 6 over x plus c. I'll call this c1, this c2. And then the last term is negative sine x. And the antiderivative of sine is negative cosine. So it's minus negative cosine plus c, which would be just cosine x plus, we'll call that c3. So now if I put it all together, here's what we have. Capital F of x would just equal e to the x minus 6 over x plus cosine x plus c. Now, the reason I didn't write plus C1, plus C2, plus C3 is because no matter what those constants are, we could combine those like terms and add them up to, guess what it would be? A constant, okay? You don't have to go through all these steps to show the antiderivative. I could have very easily just said the antiderivative is capital F of x equals e to the x minus 6 over x plus cosine x plus c. Now, I put the double barred arrow here to just say that implies that capital F is that. You don't want to ever put that like little f equals the big F for its antiderivative. Okay? All right, guys, that's it for this one on antiderivatives. Hope that was helpful.